Hello, and welcome back to the course Physics 123 Quantum Mechanics 1. We are now on our last chapter of this course, and we will have an example which will summarize all of the lessons that we have learned in this chapter. So before we proceed, let us review uh, what we have discussed so far in this chapter. So we have discussed about the Schrödinger equation, which is the equation of state, where our state is the wave function psi, and we have generalized the form of the expectation values for continuous variables. So if you have a physical quantity q, which is in general a function of position and momentum, then the expectation value or the average value or mean value of that quantity is just obtained by differentiating psi star, q, and psi. So you sandwich the operator form of your physical quantity between psi star and psi. That's the generic form to find the expectation value of a physical quantity q. We also have discussed in the previous lessons about standard deviation, which represents uncertainty. And we will relate that to our last topic for this session, which is all about the uncertainty principle. So you may have discussed the basics of uncertainty principle in your modern physics, which maybe one uncertainty principle that you have discussed is the uncertainty between position and momentum, and we will focus with that in this chapter. So we will generalize. We will not be deriving the uncertainty principle in this lesson. Instead, we will derive the generalized uncertainty principle when we formalize the discussion of quantum mechanics in chapter 3. So let's start our discussion with position and momentum, quantum position and quantum momentum. So for instance, your probability density, absolute value of your wave function squared, or absolute value of psi squared, probability density will looks like this. So in this example, your position is indeterminate or undefined because there are many possible positions here. Your x could be here, or here, or here, or here, or here. Based on this example, you have 1, 2, 3, 5 peaks, so five possible probable values. Now, if you transform this in k-space by doing a Fourier transform, so you transform from the position space to k-space. So take note, x is position, k is what we call the wave number. It's actually equal to 2 pi over lambda. X has a position of length, say meters. K has a position, K has a unit. X has a position of length or meter. K has a position of 2 pi over lambda, so 1 over length, or say 1 over meter, or meter inverse. So this is in your solid state physics, you usually call the k space as the reciprocal space, because the units in that space are reciprocal of length, so reciprocal of position. So in your modern physics, you have discussed about the quantum mechanical result of momentum, wherein momentum is just h bar times k. So meaning, since h bar is just a constant, if you multiply your wave number by h bar, by a constant h bar, then that becomes the momentum. So essentially, k and momentum are the same because they're just related by a constant. Similar when we say energy is just equal to mass, because they are just related by a constant c squared. So energy is just essentially mass. So here, momentum is essentially wave number because they're just related by a constant h bar. So when you Fourier transform to the k space, it's actually just transforming to the momentum space because you just multiply your k values by h bar and they become momentum. So when you Fourier transform this wave function, probability distribution psi squared, into the momentum space, it will look like this. So your momentum, your wave function now is momentum space wave function as a function of momentum and t, p and t. And it will look like this. The momentum will now become defined. So you can actually think of this as a wave. This is a wave, right? So a wave has a wavelength, lambda. So if you have a wavelength lambda, then based on de Broglie's hypothesis, then if you know the wavelength, the quantum wavelength for that matter, then you will know the quantum momentum. So here, you don't know the position, but you know the wavelength. So you know the quantum momentum, or the momentum is defined. Conversely, if your position space wave function psi as a function of x and t squared, the probability distribution will look like this. It's defined for a certain value of x, say x naught. So usually this happens when you measure the position of the particle. So when you measure the position of the particle, the wave function actually collapses into one or close to one value of x, such that the particle takes a stand, or you're actually confining the particle to one position. That's actually what measurement in the quantum world is all about. So when you measure the position of the particle accurately, when you transform that into the Fourier space, so you measure the position, you define the position. If you transform that in the momentum space, so in the momentum space, this axis is now momentum. So you will notice that you no longer know what is the momentum of your particle. So the momentum becomes indeterminate or undefined. So that's actually what is Heisenberg's uncertainty principle is all about. So it states that you cannot measure position and momentum at the same time. So if you measure momentum, you lose information about its. If you measure the momentum of a particle, you lose information about its position. Conversely, if you measure the position of the particle, you lose information about its momentum. So there's just a limit to what you can measure simultaneously in the quantum world. So most variables in the quantum world cannot be measured simultaneously. But of course, there are variables which we can measure simultaneously, and we will discuss that in the future chapters. So this is the mathematical form of Heisenberg's uncertainty principle. The standard deviation, or the uncertainty in x, multiplied by the standard deviation or uncertainty in p in momentum, must be greater than or equal to h bar over 2. So this is the limit. So you will notice that h bar is the Planck's constant. It has a in the orders of magnitude of 10 to the negative 34. In the classical realm, h bar is actually very, very small, 10 to the power of negative 34. That's a very small number. So in the classical realm, this is actually equal to 0. which means in the classical realm, you can simultaneously measure position and momentum at the same time. But in the quantum realm, in the realm of very small objects, even though h bar is 10 to the negative 34, but h bar is a big number when it comes to the quantum world. So that is why this is significant in the quantum world, the h bar. But when you go to the classical realm, h bar is actually a very small number. So this is approximately equal to zeros. So meaning you can measure both position and momentum at the same time. So if you rearrange the equation, you will notice the relationship between the two uncertainties. They're actually inversely proportional with each other. So that is what I have been telling earlier, that if the uncertainty in x is very small, meaning very small standard deviation, very small spread from the mean, so say your position is defined very small standard deviation in x, then your momentum, since they are inversely proportional, then the uncertainty in momentum will be large. So small sigma x will correspond to a large sigma p. And inversely, if you have a large sigma x, large uncertainty in x, then you will have a small uncertainty in momentum. So they are inversely proportional. So meaning, if you have if your position is accurate, your momentum will not be accurate. If your position is not accurate, your momentum will be accurate. So that's what Heisenberg's uncertainty principle is all about. Okay, so this will be the last topic for this chapter. So for our example, we will now have an example which will incorporate all of the lessons that we have discussed so far for this chapter. So this problem is like the complete problem for this chapter. So suppose you have a particle of mass m, and it is in the state given by this wave function. So notice that our wave function here is now a function of x and t. There's now a time component. So where capital A and small a are positive real constants. So you are asked to find a, the normalization constant. So you normalize your wave function. So for what wave function, for what potential energy u as a function of x does this wave function satisfy the Schrödinger equation? So what's the potential energy if your particle is in this state? So you need to use the Schrödinger equation for letter B. And you are asked to find the expectation value of x, x squared, p, and p squared. So of course, if you know the expectation value of x and x squared, you can find the uncertainty or standard deviation in x. If you know the the expectation value of p and p squared, then you know the standard deviation in p or the uncertainty in p. So you find that in letter D and check for the consistency of the uncertainty principle. Do they violate the uncertainty principle or not? Okay. For this problem, there will be a useful formula. Actually, this is a very useful formula in this chapter and the next succeeding chapter. This is sometimes called the Gaussian integral formula. So if you encounter an integral like this, where m and n are integers, and it can start from 0, 0, 1, 2, 3, 4, 5, 6. So it's just equal to the gamma of 2n plus 1 over 2n times n beta, where beta is just a constant here, to the power of 2n plus 1 over 2n. Again, we have discussed about the gamma function. It's just related to the factorial function. And the gamma of 1/2 is actually square root of pi. So using this relation, gamma of v plus 1 is equal to v gamma of v, The gamma of 3 halves is essentially gamma of 1 half plus 1, so it's just 1 half gamma of 1 half, or square root of pi over 2. Okay. So for the first problem, you are asked to find A, the normalization constant. So we use the normalization condition. So instead of using absolute value of psi squared here, we use the more general form of absolute value of psi squared, which is psi star psi. Okay, sorry. So let me just I forgot to place the wave function here. So let me just copy our wave function psi as a function of x and t. It's a exponent of negative a mx squared over h bar plus it. So this is our wave function. Okay. So we use the normalization condition. So we take the integral of the conjugate of this. So you have I. So when you take the conjugate, this becomes negative I. When you take the conjugate. So you will notice that this is actually, you can actually write this as two exponentials. So you can actually write this as negative e to the negative. So you have a e to the negative amx squared over h bar, and then the second exponential is a e to the negative iat. So you can actually write it like this, two exponentials. So when you take psi star psi, you will notice that since this is a real, then its conjugate is just itself, so it's just a squared. So also the first exponential is also real, there's no imaginary here, so it's just conjugate, its conjugate is just itself, so psi star times psi is just the square of that one. So you will have e to the negative 2, say max squared over h bar. But here the conjugate of this exponential term is e to the positive iat, and its original form is e to the negative iat. So you multiply those two, e to the iat times e to the negative iat, and you will get e to the 0 or 1. So the time in this case, the time component will actually cancel each other out. So actually in most of our examples, when you take the absolute value of psi squared, where psi is a function of x and t, it now only becomes a function only of x. The time component most of the time cancels each other out. But note that this is not a general situation. It's just there are still some examples when you take the probability density and it's still time dependent. So for this case, this is true for our example. Okay, so this is our absolute value of psi, and in our integral you will get, so I will take out the constant a squared from negative infinity to positive infinity of e to the negative 2 ma over h bar x squared dx, and it should be equal to 1. Okay, so I will go back to our integral formula, our Gaussian integral formula, which is this one, and compare. So we will use this formula, and by comparison we see that m is equal to 0 because there's no x here, so meaning m is equal to 0, x to the 0 is 1, and in this case our beta is 2ma over h bar. This is our beta, and our n is equal to, so this is x squared, this is x to the 2, and meaning n is equal to 1. So therefore, based on the formula, this integral is just gamma of 2m plus 1 over 2n. So m is 0, meaning 0 plus 1, so 1. Gamma of 1 over 2n, n is equal to 1, so gamma of 1 half, all over beta, which, so n is just equal to 1, so n is just equal to 1, and beta is this one, 2ma over h bar. So 2ma over h bar to the power of this one, 1 half. Okay, so gamma of 1 half is just this one, square root of pi. So this is just actually equivalent to the square root of pi. So simplifying, since we have already evaluated the integral, simplify. So you get a squared is something like equal to some value, you take the square root, and you will get this value here. So a is equal to the fourth root, 2ma over pi h bar to the power of 1/4. So our wave function will now look like this. So we replace our normalization constant a with the value that we have obtained here. Okay. Second question. For what potential energy does our wave function satisfy the Schrödinger equation? So we recall our Schrödinger equation. So we actually know the form of psi. Psi is known. It's a function of x and t. The only unknown actually in our Schrödinger equation is u. So essentially, we solve for u given our psi. So therefore, we need to find partial of psi with respect to t, and the second partial derivative of psi with respect to x, and then solve for u. That's what we will do for this problem, or that's how we solve this problem. So given our psi, so we integrate with respect to time. So integrating with respect to time, given our psi here, this is our psi. So take note that we can write our psi as a function of x and t as, I will just write this so that it will not be lengthy. I will just write out this constant here as a. Then you will have e to the negative max squared over h bar. This is the x component in this exponential, and then e to the negative iat. This is the time component. So if you take the derivative of this with respect to time, you are actually only taking the derivative of this term here. So what's the derivative of this term? So the derivative of this term is just of any exponential is e to the u, derivative of u, the power. So you will still get a e to the max squared h bar e to the which negative iat. You will still get this term when you take the derivative, which is just your psi, and then the derivative of this term with respect to t, which is just negative ia. So therefore, partial of psi with respect to t is just negative ia times psi. Sorry, that one. Now you do the same for x. You take the first derivative first, and then you take the derivative of the first derivative to get the second derivative, and you will obtain this expression here. So I will just leave the differentiation to you because this is just elementary differentiation. There's nothing complicated yet. Okay, so if you substitute partial of psi with respect to t back to our Schrödinger equation here, and you substitute the second partial derivative of psi with respect to x, which is this expression, substitute it back here and solve for u, then you will get this result. So I will leave that to you because that's just simple substitution, simple algebra. So the result is this one. So it's a quadratic potential 2 ma squared x squared, where a is a constant, m is the mass of the particle. So let's now find the expectation values of x, x squared, p, and p squared. So for the expectation values of x, we sandwich x between psi star and psi, and since our psi star psi will just look like this, and this is an even function, so if you multiply it with x, it becomes an odd function, an odd integrand, even limits. That's why it's automatically 0. So it's an odd integrand. Okay, but not for the case of x squared. For the case of x squared, it's now an even integrand, even limits. So in the case of x squared, you will have something like x squared. In the case of the expectation value of x squared, you will have something like, so you take a squared. I will just substitute a squared later, even though we already obtained the result for this. So your integral will look like negative infinity to positive infinity of x to the x squared e to the negative 2 ma x squared dx. So that one. So this integral actually looks like our the integral formula for the Gaussian integral formula before. So in this case, if you will recall, the Gaussian integral is from negative infinity to positive infinity of x to the 2m e to negative beta x to the, sorry, this should be an h bar here over h bar, beta x to the 2n. So the Gaussian integral looks like this, and it's just equal to the gamma of 2m plus 1 over 2n over n times the beta to the power of 2m plus 1 over 2n. So that one. That's our integral formula. So you use that integral formula to evaluate this expression. So from here we see that m is equal to 1 and n is also equal to 1. So you use that integral formula to obtain this value, h bar over 4 ma. So how about for the expectation value of p, momentum? So we haven't yet had any example for the expectation value of momentum, so we will try that out first. So this is our formula for the expectation value of momentum. So psi star has a term a, and psi also has a term a, so I will take out that of the integral, the constants. So what's left in the psi star is the exponential parts. So if we take the conjugate, so you will get e to the, I'm just gonna go back to that, I don't know, e to the negative ma x squared over h bar, and the conjugate is e to the, so that's negative ait or iat, therefore negative I becomes positive I, so iat. This is what's left of psi star. I already took out the constant, normalization constant a here. And then we have from our formula our momentum operator. So I will take out h bar over I outside, so there will be an h bar here, sorry, over I, and then I will, the partial derivative with respect to x, the differential operator will act on what's left of this quantity here, psi. So what's left is the original version, not the conjugate. So you have e to the negative ma x squared over h bar e to the negative iat. So there's a dx here. Okay. So since we are all only differentiating with respect to x here, then we can actually take the time component here out of the differentiation and multiply it with this, and you will notice that something like this one and this one will just be equal to e to the 0 or 1. So the multiplication of e to the iat and e to the negative iat is just 1. So in order to evaluate this, we first need to know what is this differentiation with respect to x. So the differential of e to the u is just e to the u differential of u. So our u here is negative ma x squared over h bar. So therefore, this differential is just equal to negative ma x squared over h bar times the differential of ma x squared over h bar, which is x squared. So you have negative 2 ma x over h bar. Okay, so the differential operator has already been applied. So this term here and this term here, we can add their powers, and we are left with x. There's an x here. So in the integral, in the evaluation of this expression, we'll have some constants outside the integral, and then the integral of x e to the negative 2 ma x squared over h bar dx. And again, since you are integrating from negative infinity, negative infinity to positive infinity, even limits, but the integrand is, since this is just x, an odd function, the integrand is odd, and even the limits are even, then this is automatically 0. You don't need to evaluate this. So it's 0. So the expectation value for momentum is 0. So you do the same for the expectation value of p squared, but this time you now act the momentum operator twice on psi. So the p squared operator is just this operator acted twice. So if you act this twice, you will have h bar squared and I squared. I squared is negative 1, so that's negative h bar squared. And then if you act the derivative twice, then you have the second derivative. So you need to find the second derivative of psi first before you evaluate this integral. So you do that. I will leave that to you, and you will get a value of ma h bar. Okay, so you now know the expectation values of x, x squared, p, and p squared. Again, the meaning of this expectation value is that the values of x, there are values of x that's positive, there are values of x that's negative. That's why the average value is in the middle, in 0. The same is true for the expectation value of p. So find the uncertainties in position and momentum, and is their product consistent with the uncertainty principle. So therefore, we use the uncertainty formula. For x, it's just the expectation value of x squared minus expectation value of x squared. So since this is 0, it's just the square root of the expectation value of x squared, or square root of this term here, which is just this one, 1/2 square root of h bar over ma. And the same for p, you will get just the square root of this, which is square root of mh bar, since this term is 0. So to check if the uncertainty principle is not violated, then we use this equation and check, is this true? is their product, or is the product of their uncertainties greater than or equal to h bar over 2? So we have a question mark there because we're trying to prove if it's if their product is consistent with the uncertainty principle. So if you multiply these two terms here, you will actually get a value of h bar over 2, which is consistent because this is greater than or equal to h bar over 2. So it's equal to h bar over 2. So the product of their uncertainties is consistent with Heisenberg's uncertainty principle. So it doesn't violate the uncertainty principle. Okay. So this is the generic problem for in quantum mechanics. So you will have normalization problem, you find the expectation values, you find the probability, you find the potential energy corresponding to your state or your wave function. But there's still one problem that we haven't solved yet, and that is, what if you are given the initial wave function and you are asked to find what's the wave function at any time t, psi as a function of x and t. So how do you do that? So the answer to that question will be discussed in the next chapter, in chapter 2, wherein we will discuss about the time-independent Schrödinger equation. So we'll try to solve, given the initial wave function, we will try to get the wave function at any time t for different types of potential energy. So that will be our lesson for the next chapter, and this ends the chapter on the wave function. So far we have discussed some basic properties of the wave function, but when we go to chapter 3, we'll now formalize our wave function such that it's not just a wave function in position space. In fact, the wave function can be formulated in position space, or in energy space, or in momentum space. So that's the end of this chapter, and I will see you at the start of chapter 2, which is on the time-independent Schrödinger equation. So I will see you next session.